Hi there. This video is for lesson 1.3, First Principles for Calculus and Vectors. All right, so here we go. So this is where I feel this course is truly going to begin. The concept of differentiation, which is a big part of calculus, one of the most fundamental and powerful operations of calculus. It's a concept that was developed over 100 years ago by Sir Isaac Newton, you may have heard of him, and Leibniz. The output of this operation is called a derivative. So what we're going to look at now is essentially the instantaneous rate of change combined with the concept of a limit. Okay? So the derivative of a function can be found using the first principle definition of the derivative. We have to start here using the first principles. Is it long? Is it tedious? Yes. This is to teach you the concept of what a derivative is before we can apply any derivative rules. Okay? Which we will do later on. So first off, what is the first principles definition of a derivative? So what this is saying is a derivative, which is denoted or represented by this notation, f prime of x, okay, or f prime of a. So f prime of a or f prime of x is the derivative of a function f at x equals to a. And what exactly is that? Well, essentially what we're trying to find is the instantaneous rate of change as the limit of h approaches 0. So let's just give you a visual real quick. So remember our instantaneous rate of change that we talked about in our first video? So what we're essentially trying to do is we are finding the slope of a secant line. Okay, so this would be a secant line. And the slope of the secant line gives us our average rate of change. For the instantaneous rate of change, we want the interval to be smaller. So let's say we care about this point right here. We want this interval to be smaller. That's not small enough. Get rid of that. Whoops. Let me draw that back. We want this interval to get as small as possible. Okay, so that orange line I drew was not small enough. Sorry. Okay. So we want the interval to get smaller and smaller to find our instantaneous rate of change. In fact, the example I used was it needs to be so small that they are practically beside each other. So let me just redraw this. This is a terrible drawing. Okay, so say I want to find the instantaneous rate of change at, say, x equals to, I don't know, 3. Okay, so which means I need to, this is a tangent line. Okay, tangent line. I need to find the slope of this tangent line. Or in other words, find the average rate of change between 2 points that are so close together, like practically touching, that it's a good estimate to our tangent line. Okay, so just to reiterate, the secant line, which is connecting two dots. Okay, as these two dots I just drew get closer and closer and closer and closer and closer to the point where these 2 points are touching, we form what we call our tangent line. Okay, the slope of a secant line gives us our average rate of change. The slope of our tangent line gives us our instantaneous rate of change. So we use the slope of a secant line to approximate the slope of a tangent line. Okay, so what we're trying to do then is find two values that are so small, so 3 or 3.01 or 3.001 or 3.0000001, okay, such that as h gets very, very small, h being the difference between 3 and the number right beside it, the limit as h approaches that, so in this case, approaching 0, okay, because 0.001 or 0.000001, this difference between these two values becomes very small, such that the slope of the tangent line will give us a good estimate of our instantaneous rate of change. Okay, so if I were to draw that again, So if I wanted to find the rate of change of x, let's say, I don't know, let's make up a number. Let's just say 3 again, okay? At 3, then I can use 3.01, 3.001, 3.0001, 3.00000001 as h gets closer and closer to 0, which h is the difference between 3.001 and 3. So in other words, 0.001. As it gets smaller and smaller and smaller, calculating this limit will give us a fairly accurate representation of the instantaneous rate of change. Okay. Now, in terms of notation, there are a couple ways you'll see this, and I'm sure many of you have seen this before in textbooks or any kind of calculus work. You would have seen these three notations. F prime of a just means the instantaneous rate of change, or the derivative of a, the derivative of f at a, dy dx. Dy over dx means the same thing. Dy by dx just means the derivative of y, okay, at x, and then y prime again just means the derivative of y. These notations all refer to the derivative of a function of at a point, which means the slope of the tangent line or the instantaneous rate of change. Here we go. Example number 1. Determine a derivative using the first principle's definition. Okay. State the domain of this function. So this is just a parabola. So the domain is x is an element of the real numbers. Use the first principle's definition to determine the derivative of x squared. So we are going to do that. So the derivative, I can either use f prime of x or dy dx or y prime. I'm going to use f prime of x. So f prime of x is equal to the limit as h approaches 0, okay, of, let me just rewrite it, f of x plus h minus fx all over h. All over h. Okay, so this formula was just copied from up here. Obviously, instead of a, it's h. Or, sorry, up here. Okay? Sorry, instead of a, it's x. So now I just sub it in. Okay, so limit as h approaches 0. Now, what is fx plus h? Well, first off, I know what fx is. Fx is x squared. Okay, so I'm going to replace that first. Okay, x squared. Now, what is fx plus h? Well, fx plus h, all I'm simply doing is replacing the x in our function with x plus h. So in this case, it's going to be x plus h squared. Okay, so then over here, I'll have x plus h squared minus, and then this whole thing is going to be over h. Okay. Now this gives us limit as h approaches 0. So then expanding this, okay, so that is x plus h times x plus h. Foiling that, or expanding it, will give us x squared plus xh plus xh. So in other words, 2xh plus h squared. And then I'm going to keep that green, minus x squared. Okay. And then that will give us limit as h approaches 0. So the x squares will cancel out. Okay, x squared minus x squared. Then I have 2xh plus h squared over h. Okay. Now I'm going to then cancel out all these h's. So there's an h there, h there, h there. Okay, which now gives me limit as h approaches 0 of 2x plus h, and then there's no h underneath. Okay, so now what I can do is sub in h. Okay, solve for the limit. So by subbing in h, I'm going to get just 2x. Okay, so that will be the derivative of x squared. Okay, now what does this value, what does it even tell us? So f prime, so let me just erase this right here, give us some more space. What this value tells us is, so f prime of x is going to be 2x, okay? Where fx is, the original is 2, what was it, x squared, I think, right? It is x squared. It is x squared. So what does this even tell us? What this tells us is, so if I have a parabola, okay? So this is the original, right? fx equals to x squared. And let's say I wanted to find the instantaneous rate of change at 3. Okay? This will tell me the slope of the tangent at that point. So f prime at 3 will give me 2 times 3, which will give me 6. Which, what does that 6 tell me? Well, if I were to draw a tangent at the point 3, so the slope, the tangent will only touch at the 1 point, okay? It's technically 2 points very close, but we're going to say it's 1 point. That means, let me just do a better job of drawing that. The slope of this orange line is 6. Okay, so I know that for a fact. The slope of this orange line will be 6, the slope of the tangent at 3. And this will now work for any instantaneous rate of change that you want to find at any given point. Okay, so for example, let's say I wanted to find the instantaneous rate of change, okay, or in other words, the slope of the tangent, which mean the same thing, at, let's say, -2. Okay, so -2, I want to find the slope of the tangent, or the slope of that green line, or I want to find the instantaneous rate of change at exactly -2. Well, sub in -2 to the derivative gives us -4. The slope of that green line, the green tangent, will be -4, or the instantaneous rate of change will be at -4. Okay, so let's dive into it. Find the derivative of ft of this function, okay? F prime of t. So again, by definition, the derivative is limit as h approaches 0, okay, of fx plus h minus fx divided by h. Well, this is our graph, okay? So let's first find the derivative. So this will equal to limit as h approaches 0. Okay, so again, fx is just whatever the original was. Root t, so I know it'll be minus root t. And then what is f of x plus h? So again, I just take whatever the function was. So x plus h. Well, in this case, it's technically t plus h. And it's a square root function, so then it's just t plus h. So then I'll have t plus h. Ooh, I see radicals. So as soon as I see radicals, which are the square root signs, okay, I should be thinking of the conjugate method, which we talked about in our last video. And so our job is now to simplify that, okay? Now I can't solve this limit as is. Why? Because if I sub in h for 0, I'm going to be dividing by 0, which I can't do. Okay, so now I'm going to multiply the top and the bottom. Okay, so the top, t plus h plus root t. By the same thing, just switch the sign. Okay, so this is called the conjugate method. And the point of doing that is to get rid of the radicals. I'm going to do the same thing underneath. T plus h plus root t. Okay, and if you're not sure how I'm doing all this, in my previous lesson, at the very end of it, I explain how this method works. Okay, so then up top, I'm just going to have t plus h, because a square root times a square root will get rid of the square root, minus t, because square root of t times square root of t would just be t. And at the bottom, everything just stays status quo. I'm going to copy down the conjugate. So that's root t plus h plus root t. Okay, and then up top, that cancels out. The t's cancel out. Okay, once the t's are gone, I also notice the h's will cancel out as well. And all I'm left with is limit as h approaches 0, 1 up top, and in the denominator I'll have t plus h plus root t. Okay. Now at this point, if I sub in h for 0, that works. Okay, because if I sub in h for 0, that means that's gone. So then all I'm left with underneath. Now once you sub it in, okay, the denominator disappears. Or sorry, not the denominator. This limit symbol disappears, giving me root t plus root t equals to 1 over 2 root t. So that will be the derivative of this function. Okay? Derivative of this function. Now again, what does this even mean? Well, let's say, which we will be, calculating the rate of change, or the instantaneous rate of change at a certain point. So let's say I want to find the instantaneous rate of change at exactly 2. Okay? And again, the instantaneous rate of change is how quickly or how slowly, if we're talking about time, something's changing at a very particular moment. So picture pouring water into a cup. If I want to find the rate of change at exactly 2 seconds, I will need to find the derivative, and which will be essentially an approximation, because I can't actually stop time in order to see how fast the water is going into the cup. So in this case, I want to find the instantaneous rate of change at exactly 2. So the instantaneous rate of change is the slope of the tangent line. Okay. So how do I find that? Well, using the derivative. So I know that f prime of x is 1, or sorry, t, I guess in this case, is 1 over 2 root t. If I want to find out what it is at 2, sub in 2, and I have 1 over 2 root 2. Okay, if I type this into a calculator, it will obviously give me a decimal, but this will give me a number. So the slope of this tangent at 2 is 1 over 2 root 2, or the instantaneous rate of change at 2 is 1 over 2 root 2. Okay. Obviously, there's no context here, but let's say it was the volume over time. Yeah, then it will be, it's draining at a rate of 1 over 2 root 2 centimeters cubed per second. Okay. All right. And what's this other picture? So this function over here represents the derivative. Okay. Right here. So the derivative is the dotted line, and this is the function itself. Okay. So I'm just going to graph it on Desmos just to show you. Desmos. I think I have it open somewhere. So then, square root of 2, not 2, sorry, x, that was our original function, okay? And then our derivative is 1 over 2 square root of x, our derivative. In this case, I obviously use t, okay? So the blue represents our derivative. I know it doesn't look the same because it's zoomed out, but if I just move it, there we go. So the red represents the original function. The blue represents the derivative. Okay. So going back to the example we used, what's the derivative of f of 2? If I put this into the calculator, it'll give me roughly 0.35. something. So 0.35355. Okay. All right. Here's another example, and let's see if I should include these in the video. This one is a little bit harder, but now I am watching the time of the video. I'm trying to keep them at around 20 minutes. Okay, so I'm going to post the solutions to example 3, 4, and 5 as well. Okay, so you can take a look at those. I'm not going to include it as part of this video. It's pretty much the same process as what we just did up here. Okay, and prior to that, if you have any questions, shoot me an email. I'll be more than happy to further explain it to you. Okay, and if I find that a lot of you are wanting more clarification in this answer, I'll be more than happy to record a video for the second half. Okay, all right, take care.